There are then 3 factorial ways, and that's where we multiply by 3 factorial ways to permute the 3 groups of employees, or you might say 3 factorial ways to permute S, C, and T as labels on the groups that you've already made. Okay, 2 more, 19 and 20. 19 says the people in charge of a raffle are going to give out 4 prize bags to the raffle winners. They want to make sure that each prize bag contains at least one of the 11 gift certificates for a department store. In how many ways can the prize bags be prepared, assuming that all the gift certificates are of the same monetary value? Okay. So, what do we have? We have 11 gift certificates, and the gift certificates are all exactly the same. We have 4 bags, and the task is to place the gift certificates into the 4 bags. The bags are just kind of sitting there on a table or whatever. The bags are not important. How many ways can we do this? So here we have objects indistinguishable, containers indistinguishable, but they don't want to have someone be a winner and then get handed an empty bag. And so we want to exclude the empty set. Well, I think this is just P11 for boom. That's exactly it, right? Split the 11 objects up into 4 piles. Yep. Okay, last one, which I'm going to squeeze in right here, number 20. Meg decides to throw her 10-year-old Sue a birthday party and allows her to invite 15 friends to the house. Notice, Gus, it says invite 15 friends. So that means 15 friends are coming, including Meg herself. We got 16 kids now. Meg purchases 25 red balloons for the children, presumably all indistinguishable, the red balloons, since red is Sue's favorite color. In how many ways can the... So, what do we have? We have 16 kids, and we have 25 red balloons. Question. In how many ways can the balloons be distributed to the children at the birthday party, including Sue, assuming that no child should go home without a balloon? Okay, well, if we need to distribute the 25 red balloons to 16 kids, but every kid must get a balloon, then the first thing to do is to pass out a balloon to every kid. So pass out one to every kid. And so now there are 9 red balloons left. And once you've given at least 1 balloon to every kid, then you may do whatever you want with your final 9 balloons. And so those balloons being indistinguishable from each other, this just spoils down to stars and bars with the 16 kids. Think of the 16 kids as being 15, being divided up into 16 regions by 15 bars, and then you got your balloons are 9 stars, so that gives you, and then every different way of ordering those symbols gives you a different way of passing out those final 9 balloons. So that's 15 bars and 9 balloons, that's 25 characters, and so this is 25 choose 9, or 25 choose 16, same thing. Okay, good. Those were like the easy problems, basically. Oh my god, that took so long. Those were the easy problems, not theoretical. They required only reading comprehension and an understanding of what partition numbers are and Stirling numbers are. And once again, the fun part is kind of discussing these back and forth and seeing how people maybe did wrong things or possibly made different assumptions, but we didn't get to have that fun exactly here. Okay, then the much more difficult part of the homework, I guess, is everything else. Okay, so let's go. Page 419, I also assigned these other 3 problems, 2, 3, and 4. I think I actually assigned 2A, but I'm going to do 2D. It's almost exactly the same, but 2D is a little bit harder, so I think it illustrates what's going on a little bit better. Okay, and we did a little bit of this in the video, or we started to do it in the video, but then we just didn't. So what does 2D say? It says, use theorem 8.2 and table 8.47 to calculate the following values of P and K. Whew, okay, and so the goal is compute P10.4. And well, what does P stand for? The number of ways to divide 10 up into 4 piles. Okay, you could probably just figure this out and be very, very confident of your answer by just going through every possible case. But of course, humans are infallible, so you need some sort of algorithm, and there is one. In particular, Theorem 8.2, as Gossett refers to it, is the what he calls the recurrence relation, or the recursive rule for these partition numbers. And here is that rule. It's P n k is, well, I just know it, but okay, P n minus 1 k minus 1 plus P n minus k k. Okay, and the way we discussed this in the previous video is, if you have a bunch of puppies, specifically n of them, and you want to put them into precisely k piles, then here are how many ways there are to put those n puppies into k piles. Well, you decide whether you're going to allow there to be puppies that are alone in a pile. And if a puppy is alone in a pile, the puppy will be sad. So if there is going to be at least one puppy alone in a pile, so consider partitions for which a lone sad puppy exists in one of the piles of that partition. Well, if that's the case, then once you tell me that a puppy is going to be alone, then the problem boils down to just distributing the n minus 1 puppies to the remaining k minus 1 piles. So there are this many ways to distribute n minus 1 puppies to k minus 1 piles, and by simply adding another pile with one puppy in it, that produces a partition of n puppies into k piles, where at least one pile has one puppy in it. But on the other hand, if no piles have lone sad puppies in them, then we can be sure that every pile contains 2 or more puppies. Well, if every pile contains 2 or more puppies, then how can I count how many ways there are to do that? Well, first I just put one puppy in every pile. Having put one puppy in every pile, and there are k piles, I just used up k of my puppies, so there are n minus k puppies that remain to be distributed to those k piles. And so the number of ways to divide n minus k puppies up into k piles is the number of ways to finish off, so to speak, a disbursement of puppies into piles in which no pile will have just one puppy in it. Okay, that was a reproof, not sure that was warranted in this situation, of this recursive rule. And now we're going to do the fun part, which is just by hand cranking out various recursive computations. What do we know? He says, Gossett tells us that P n0 is 0 and P n is 1. I find this to be kind of an obnoxious thing to say because well, I just don't see why I ever need to know that why don't you just tell me what Pn1 is? Of course there are 0 ways to disperse k. Of course there are 0 ways to disperse of course there are 0 ways to divide n puppies up into 0 piles. That doesn't seem very useful to me. The thing that I kind of want is to know what Pn1 is, and it's just obvious from the definition of these partition numbers that Pn1 will be 1, because there's just one way to divide n puppies up into one pile. You just put them all in one pile. But if we wanted to sort of use the theorem on Pn1, well, what would you get? You would get that it was Pn minus 1, and then we take 1 away from there, 0, which according to this is 0. And then what are you left with here? You're left with P n minus 1, P n minus 1, 1. Now that's just 0 by the base case of this recursive rule, and this just drops down by 1. And then if you just do that, like, n minus 1 more times or something, you'll eventually get down to P11, I suppose. and then I'm supposed to say that that's just 1. So okay, what am I rambling about? What I'm rambling about here is that I don't like this. I find that this base case, though technically it's sufficient, is like for user purposes kind of a drag. So I would like to. I'm going to claim that I just proved by talkie induction that in fact this is a kind of a better, more human base case to be in possession of. That the number of ways of putting n objects into one pile is just 1. Okay, this is the theorem. We weren't being asked to reprove it, but I kind of just did reprove it by talking it out. And this is with my new base case that I prefer. It's not exactly what Gossett wrote. Okay, what's the rest of this problem? I didn't even finish reading it yet. It says calculate the table 8.47. All right. Now a hilarious wild goose chase ensues regarding the existence of table 8.47. You might be asking, what the hell is table 8.47? Well, it turns out that table 8.47 is on page 499 of the textbook in the end of chapter 8, wherein Gossett has the solutions to the various quick checks that he disperses throughout the chapter. And actually, here is what this table looks like. It says it has a thing for every 1. So here's the way he sets it up is like this is n and this is k. And so n could be 1, 2, 3, 4, 5, 6. His table goes up to 6, so R will too. Ours will too. 1, 2, 3, 4, 5, 6. Okay. Yeah. And now what we're supposed to do, this was literally the homework assignment, or rather, what we were supposed to do in the quick check for which this table is the solution, the quick check itself exists on page, page 409. The quick check says, dude, fill in this table. And the table on page 499 is just the solution. And so I think, if we're being honest, we should just fill in this table now. Oh, another thing he mentions, he sort of builds into this theorem, which is also kind of stupid, is that P n k equals 0 if k is greater than n. Like, okay, sure, man. That's definitely true. If you have n puppies and you want to put them into more piles than there are puppies, well, you just can't do that. And so what that says is, when k is bigger than n, it's just like no. So, all right, what does that mean? That means we just can't have stuff up here because this is k and this is n. So, okay, so we just kill this. Oh yeah, just enjoy the tedium of it all. So great. All right. And then also PNN is 1. Okay, that seems just reasonable. So this is 1. Right? If you are going to put n puppies into n piles, and you just put 1 puppy in each pile. In each pile. And so we have these 1s. And then now is where I really want to have this. That PN1 is 1, so I can just put 1s here everywhere. Okay, and that's about all of the table that I can do without doing any sort of thinking. Let's fill in the rest of this table right now. How do we do it? Okay, so we need to be here, right? So this is like P32. Well, what is P32? P32 is P21, which is just 1, plus P. This is going to be terrible, I think. What did I just say? P32. P32 is P21. Yeah, that's right. Which is 1 plus P12. That didn't work. That wasn't what I thought was going to happen. P32. Ah, shit. P32 is P32 is P21, which is 1, plus P. Why is that 2? Oh, bad video alert. Bad video alert. Maybe I'm just wrong that's, wow. Yeah, it's just wrong on my paper. Good thing it's not wrong in the back of the book. That is just indeed a 1, according to Gossett and according to the logic I'm doing right now on the spot, as opposed to the logic on my paper. Okay, good. Let's keep going. What goes here? P42. P42 is P 3, 1, which is what's here, plus P 2, 2, which is 1. So we get these two. So that's 2. P43 is going to be P 3, 2. In other words, you want to kind of add two numbers. You want to add the number which is here to some other number, Pn minus Kk. So you want to go, there's some like cool geometric way to do this like really fast. Let's see, I want to do P1, what's the answer? P43, so I want to do P1, 3, which, so this must be a 1. Geez, I hope that's right. Is that right? Yeah. Okay, so P3, 1. I don't know. Okay, it'll come to me in a second. What goes here? That number plus P32, and P32 is 1. So this is also going to be a 2. What's this? P53 is going to be that number 2 plus P23. So that's going to be only a 2. What goes here? 1 plus P14, so that's going to be just a 1, because it's just that number. And now I think things get like a little bit exciting. What goes here? It's going to be that number plus P42. Oh yeah, so I guess I go up by what row I'm in or something like that. I go up the column by whatever column I'm in. So I go up 2. So it's that number plus that number. So that's going to be a 3. Let's test this. It's going to be that number plus, now I go up 3 because I'm in column 3. And that's going to be 1. So it's also a 3. This is going to be 2 plus, well now I'm in column 4, so I go up 4. So this is going to be just 2. And here I go up, so this is going to be just 1. So, okay, this is just so dumb. I can't believe I'm doing this. Well, I did it. Now we get to do the actual problem, which is, what's P10 for? Gossett says, yo, just use this chart on page 499, and I don't take kindly to that kind of just use the chart. I need to make the chart, man. Well, now I have done it. What's P10 for? Well, according to the recursive rule, this is going to be P93 plus P64. Oh man, I don't know P93. Do I know P64? I do. It's 2. Okay, what's P93? Well, P93 is going to be P63 plus P. No, not P63. P84. I meant P82. I meant to say plus P63 plus P64. And also P63 is on my table. This seems like the most organized way to do it. And then what's P72, applying the recursive rule to what's P82, applying the recursive rule to P82, this is just P71, both drop by 1, plus P62. Alright, this is kind of dumb. I'm essentially just teaching you, this is like what you would do with a 9th grader, I guess, right? I'm just showing you like how to do recursion by hand. This might be a waste of time. Well, anyway, what is P71? I know it's just 1. This I know is 3. This I know is also 3. And this I know is 2. And so 6 and 8, 9. So the answer to this is that this is 9. Alright, well hopefully I've at least explained to you. Of course you would use computers for this if you were a real person. But anyway, that's how this recursive rule in fact enables you to just compute the partition numbers. They're sort of available to you. Okay, 3C, also pretty mindless. 3C just says, dude, give me all the partitions of 7. Okay, yeah. So I guess we're just really going to do this. So what are the options? Just 7. That's an option. I'll put a box around it. 6. That's the number of ways to do it with just one in one pile. How about if we're going to do 2 piles? Well, 6 plus 1, 5 plus 2, 4 plus 3, and that's it. Yeah. How about if we're going to do it in 3 piles? Well, now it could be 5 plus 1 plus 1, or 4 plus 2 plus 1, or 3 plus 3 plus 1, or 3 plus 2 plus 2, and I guess that's it. Yep, it is. Okay, what next? Oh, just with 4 summands. Well, then it's got to go like 4 plus 1 plus 1 plus 1, and then 3 plus 2 plus 1 plus 1. So that's 5, 6, 7. Or I can drop one of those over there, so that would be 2 plus 2 plus 1. Or I could do something else. No, that's it. Okay, how about if I use 5? Well, then it's going to look like 3 plus 1 plus 1 plus 1 plus 1. Or 2 plus 2 plus 1 plus 1 plus 1. That's the only way to do that, right? Yeah. And then how many ways are there to do it with 6 summands? Well, that's going to be only 2 plus 1 plus 1 plus 1 plus 1 plus 1. So 3, 4, 5, 6, 7. And then finally, there's the thing where you just have all 7 piles. 4, 5, 6, 7. Okay, so these are maybe 2 dumb problems. But I'm really, really spending a lot of time on these partition numbers. And, you know, I'm just really getting comfortable now with them. Okay, 2 more problems to go. Problem number 4 is just like an entire giant world. So let's do it. It's actually very fascinating, I think very hard, and it's like a whole, I don't know, if you're like of my intelligence, you know, this is like a whole half an hour or something just to do this one problem. It's like 2 big proofs. Okay. Number 4. All right. The first thing that number 4 says, in fact, he introduces what the point is. The goal of this problem is to show that P and K can also be interpreted as the number of partitions of N for which the largest summand is exactly K. Okay. Well, the first thing Gossett wants us to do is a proof. And what is the proof? The proof is that P and K is the sum from K equals 0, from I equals 0 to K of P n minus K I. Where K is something, okay, great. Okay, wow. Oh, and with base conditions, Pn1 equals 1, and Pnk equals 0 if k is greater than n. Okay. Well, okay. What are we being asked to prove? This is part A of this problem. Well, we're being asked to prove this thing which came up. Okay, I say came up like it happened by accident. I brought it up on the video when I was initially teaching these, and because it usually comes up live in class, at least someone notices that there is a these problems. Let's see, which one is it? It's the oh my god, objects indistinguishable, containers indistinguishable, empty type problems. For example, when we had the 8 blue towels and we had the 4 plastic bags that Jeff was using to carry home his 8 blue towels, you'll recall that the solution to this problem was, well, he can put all 8 of his towels in one bag, or he can put all 8 of his towels in 2 bags, or he can put all 8 of his towels in 3 bags, or he can put all 8 of his towels in 4 bags. Somehow that the partition numbers are designed to talk about non-empty containers. And so when the containers are allowed to be empty, you have to sort of casework through how many piles have something in them. And yet, we noticed that this is actually just P12.4. Okay, so actually I feel like I've talked this out now twice, once in the original video and once while going over this Jeff Blue Towels problem. So maybe this proof is just sort of done. But this is the thing that we're finally being asked to prove here, although phrased slightly differently, but it's the same kind of thing. Okay, and why is this true? Why is this true? First, maybe just an example, another example of this. Okay, so take P83. And I want to express. Let's just mindlessly follow this summation here, and try to get a feel for this, because usually this is easier to do with numbers. So what is P83 according to this formula? According to this formula that we need to prove, it's starting at 0, so it's going to be P50. Okay, but I just don't want to write P50 because that's just stupid, because P50 is just 0, and I'm running out of space here. So I'm going to write P51 plus P52, and I'm supposed to stop at K, so P53. And Gossett seems to understand that that's all that matters, because he's changed his base case here to be that Pn1 is 1. That's what I was complaining about earlier. So if you don't mind, I'm just going to change this index to 1 to reflect the fact that P anything 0 is just 0 anyway, so it's sort of stupid to start counting with 0. Okay, well, here it is. Why should this be true? Well, we've already discussed this now with Jeff's plastic bags mutating into towels, and I think in the original video there was phantom Snickers bars that were borrowed from the following day's supply and then taken back away again, or something strange like that. Perhaps what we should do is go back to the original definition of these partition numbers. So what is P83? It's the number of ways of splitting up 8 into 3 piles. Well, let's just do that. So one way is 611. Another way is 521. Another way is 431. Or I could make this 422, I guess. Or I could, is that all there is? Yep. Or I could make this 332. Okay. That can go either there or boom, and then yeah, great, great. Well, question. Okay, so no question. Fine, there it is. All right, what's P51? This is the number of ways of writing 5 in just one pile. Okay, this is the number of ways of writing 5 in 2 piles. Well, that would be 4 plus 1 and 3 plus 2. I guess that's it. And this is the number of writing 5 in 3 piles. And that is 3 plus 1 plus 1 and 2 plus 2 plus 1. And indeed, okay, the theorem seems to be true, because we get 5 on the left and 5 on the right. So maybe if we can understand this pattern, perhaps visually or otherwise, we can get some intuition as to why this is true. That will help us come up with the combinatorial proof. Well, there are just some, in my opinion, if you sort of stare at this for a couple minutes, there are some clear relationships that emerge. In particular, 332 looks a lot like this 221. And this 422 looks a lot like this 311. And this 431 looks a lot like this 32. and this one looks a lot like this one, and this one looks a lot like that one. I should use a different color. So what's going on here is that following the arrow from the left to right, I remove one from every pile. If you think of the 5 ways there are to split the 8 puppies up into the 3 piles, if I remove one puppy from every one of these piles, then what I arrive at is precisely the piles of puppies on the right. But here the piles are not allowed to be empty, but over here they are allowed to be empty, so to speak, because you can have fewer than 3 piles. Okay, so I now sort of just deeply kind of get this, I think, in a fundamental way. Okay, so hold on. I rehearsed this in my brain before the video. Let's see what we can say. It is somehow these. It's the existence of these. What determines whether. So okay, I have PA3. What does it mean? It's the number of ways of splitting up 8 objects into 3 piles. Or if you, well, let's just leave it at that. The number of ways of splitting up 8 objects into 3 piles. Where no pile is empty. And for every one of these different partitions, it seems to get matched in this combinatorial matching argument that we're making with a partition for a partition either in P51 or in P52 or in P53. And what determines, and I've color-coded these, which partition it matches with, and it's the number of lone sad puppies in a pile. Here we have 2 puppies which are sad and alone. Here we, in the 2 red ones, we have 1 puppy that is sad and alone, and here we have no puppies that are sad and alone. And so in fact, I is the I which we are indexing by, the 1, 2, 3, the thing that's starting at 1 as I've fixed it and is going up each time, ending at K, is the number of puppy piles, or maybe I should just say the number of piles with at least 2 puppies. Yeah, the number of piles with at least 2 puppies. And if the puppies are sad when they're alone in a pile by themselves, then this is really the number of piles of happy puppies. Number of piles of happy puppies. Okay, and now we see, I think, exactly what's going on here, right? Here, if there's only 1 pile of happy puppies, wait, let's see. I want to go maybe from right to left or left to right. I don't know. I guess what I want to do is claim something like this. Claim. Both sides count the number of ways to partition 8 objects into 3 piles. Indistinguishable objects into 3 piles. For the left-hand side,